Hello and welcome to the first lesson in what will be a complete video lesson series of the entire grade 12 university physics curriculum in Ontario. So I am going to start with a review section from grade 11. It's a pretty important fundamental skill to be able to just tackle along the way, and so it's a good start for review. So we're going to look at uniform acceleration equations, working with those situations. So let's get started. So I really strongly love the this table here. I call it the UASM. It's the acronym for Uniform Equation, Uniform Acceleration Equation Selection Matrix. I call it. So UA. Oh my gosh, Uniform Acceleration Equation Selection Matrix. Woo! Anyways, you don't have to call it that if you want to, but my students seems to have stuck where I teach locally here. Anyways, the idea of this thing is if you have this, you can easily select which equation you need to use in the scenario. So for example, if you have, displacements given, you have the initial velocities given, so that's an initial velocity like VI or V1, initial, right? And then final V2, meaning final. So if I had maybe all of those things and I wanted to get acceleration, maybe this is the one that's unknown. We want to find out acceleration, right? You tell that in this equation, you've got everything except for the one you're looking for, which means you can solve for it, right? You'd have V2, V1, and the displacement, the unknown. If there's only one unknown in an equation, you can solve it, okay? So that is the name of the game of just tackling these questions head on, just using equations. So let's take a look at it. So we're going to have a car here traveling 30 meters while accelerating for 4 seconds. So when you're reading the question, not a bad idea of just pointing out, okay, there's my delta D, my displacement, and it's for 4 seconds, so that's like delta T. And so for the final velocity, so that's my V final or my V2, which is the 18, and whatever. So we got those, and then it says determine the acceleration. So A equals question mark is a required, right? So I'm essentially going to be going through the RASC process of problem solving. So you're given information, your required information. I've just been doing it in green here. And then you're going to analyze, meaning pick an equation, and then you're going to solve and state your answer. Solve and P for paraphrase, just describe your answer. So obviously, as I've already pointed out, we have the displacement. We've got the next thing I did, time was 4, and then we did the final velocity was 18, and pointed out that we are looking for this acceleration that I did in green, right? So there's your required and your GRASP process. Definitely at this point is when you're analyzing like which equation, right? And so if you know the equation, then just slap it on the board, slap it on the page and use it. But if you're wondering and you need a little bit of help, which is pretty typical of these ones, there's 5 decently complicated equations, each with 4 of the 5 variables. It's a bit of a task. So you can look at this and say, okay, well, I've got my displacements, I've got my times, I've got my final velocities, and I'm looking for acceleration. So in this case, you can see that the one that has 4, has just those 4, not something else you don't know, and so you can't use it, is that one there. And so that's here, you pick that equation. Okay. Now that equation is picked, I'm going to just show you on the bottom of this page. Actually, there's something hidden because I re-show my screen here. The equation manipulation option. Students tend to prefer putting numbers in, I think, and solving at that point, because then when you're dividing both sides by t or something, instead of being a v divided by a t or whatever the case may be, it just becomes a 6 divided by 2. It gives you 3. It just makes it seem a little simpler, right? But we are also going to look at the idea of solving for the variable you're looking for as well. It's a math skill that should be doable, whether it's your preference or not. And you'll see in the homework or practice assignment here, there's a rearrange, sorry, this one, number 17, rearrange the constant acceleration equation, from which average acceleration has been eliminated. They're saying average acceleration, really it's since it's uniform acceleration, you don't need that word here, because it's a uniform acceleration section that we're doing. So anyways, that would just be solving for a delta t and solving for a v final, right? Here we go. So we have our equation, we plug our numbers in, and I have this all worked out in advance to streamline this and make the video easier to sit through and whatnot. I do recommend though, if you're in a class, in an hour, 15-minute long class, your teacher was writing this stuff on the board, you'd be writing it down, you'd be thinking about it step by step. If you want to get the most out of this YouTube video lesson version of a course for those that are in the online course, or for anybody that's using this anywhere, you really want to process this through the brain, press pause, put those numbers in. So if I had not shown that yet, I would have said, hey, press pause and, have maybe press pause back here, wrote down some numbers, and then you press pause here and you wrote down numbers into the equation. You will get way more out of this. You'll be processing it in your brain way more, right? So here we go. What would we do? Well, there's an 18 times 4, so of course doing that would make sense. And press pause and think of the next thing, and so on and so on. I'm not going to say that all the time. It's up to you to engage and press pause to really take advantage of this if you are looking for the most learning. So here we go. That's 72, of course. We can take away 72 from both sides. And then I have, I could get rid of that 16. I pointed out here in red. Of course, I could have done the 16 divided by 2 at this point and had a minus 8, in which case I could divide by 8 everywhere, or minus 8 everywhere. But the way I did this originally, I just did the 16, but I saw it and I went for it. And then when you do that division, back up here, when you do the 42 divided by 16, so 42 divided by 16, get this number of 2.625. The best advice really is to keep all of that, 2.625, right? 625. Keep all of that until the end, and then round really at the end, and we'll probably do a review about, the specific number of decimal places and so on, all the significant digits you remember from grade 11, hopefully, but we'll have a chance to review it at some point. For now, more exciting just to get some real good stuff done, right? But I did want to just show, if you were rounding, just as an extra thing, that, should you round that to be a 3, most people would say probably, but really the actual better rounding rule is to round that to a 2. And the reason for that is because if you're always rounding a 5 out, so this 5 at the end of the 65, if you're rounding that out and you're always rounding up, then that means you're rounding up for 1, 2, 3, 4, 5, down right here, over here, 1, 2, 3, 5, and then only rounding down for 6, 7, 8, 9. And so you're rounding up more often than down, right? So banks and in science, you do calculations over large numbers and large number calculations, rounding using the more advanced rounding rule of just making the result even, right? So a 2 stays as a 2 because it's already even. If it was 6.35, it would round to 6.4, right? That way you're truly rounding up or down, half. You're rounding up half the time essentially, and down the other half. Okay, but the better rule here would just be to keep all the decimals till the end. That's, in this case, let's just leave it at that. Option 2 would have been to solve for the thing you're looking for, so solve for acceleration. So would have been the same kind of thing, right? It would have been taking away v final times time, which was what we did before, so take away 72. Just seems a little more easy to understand, right? If you take away 72 from both sides rather than taking away vt for both sides. And then, of course, we have this divide by -2 thing, right? We're going to multiply by 2, -2 that is. And then we have an acceleration, or no, sort of solving for acceleration, right? Dividing over delta t squared, okay? So we're getting, in the end here, an equation for acceleration, being this 2 delta t minus v final delta t over delta t squared. You definitely don't want to think of that as something you memorize and you start with that equation. I just really, really frown upon starting with that thing. You want to just think of that as like, if you solve for it, great, you can just go ahead and use it, but it's not something, you don't want to add it to like an equation sheet or something. Equations can be 1.5 miles long before you're halfway through a physics program. So multiple versions of every equation, be ridiculous. So here, of course, plug all those numbers in at this point and just solve, and you get that same number. Okay, so that is an intro there to that skill. A little unit analysis, just like in the homework here. I try to model in the lesson, some of the things that you're going to see in the practice assignment. So show that the units, right? Show that the constant acceleration equation for which t has been eliminated is dimensionally correct. In other words, show that the units match the way units are what they should be. If it's representing velocity, it should be meters per second, and so on. In this case, you've got units. Press pause. Put things in if you want. You have a meters in the displacement. You have a meters per second times seconds. So right here I have meters, and then a meters per second times seconds. And so essentially I've got meters in the top, and I've got seconds squared in the bottom. The only thing that's a little bit weird in your unit analysis is you might think of this as like, that doesn't become zero, right? You just think of it as like meters times, number, take away number essentially, or whatever. But I mean, it doesn't matter that it goes to zero. It was still units, like meters that we were talking about. They're both meters. Yeah, so meters per second squared, units of acceleration. That's a win. All right. Number 2 here, a boat with an initial velocity of 20 meters per second forward accelerates at a rate of -4 meters per second squared. Determine how long it will take to come to a stop. Determine how far it travels while stopping. Draw a VT graph. That's going to come back to grade 11 stuff for some people. And use the VT graph to confirm the displacement. And my VT graph use here is very strategic because it really helps you visualize the problem, which of course is how we started off in grade 11, my in-person class anyways. So here we go. Given information, we could go ahead and do the same thing, right? So we have an initial velocity of v1, and I'm not super picky about vector bars and all that in this scenario, just get it done, right? Accelerate at a rate of the -4 meters per second squared, and that's kind of all that's shown there. It says, that's all that's shown there. It says determine how long. So we could say, okay, we want the displacement or the time, as well, right? But it feels like maybe that's all you're given. And if that's the case, if you're ever stalled trying to figure out enough numbers to work with, always please do this v1, v2, acceleration, delta v, and delta t. Those are your 5 variables, right? So if you look at this situation, you're like, okay, I've got the v1, and I've got the acceleration, and I want to know the time. So you need something else. You need one of those other ones. So you have to just look at it and say, okay, well, do I know the final velocity or do I know the displacement? And so they certainly didn't tell you the displacement, but they did, of course, tell you that it comes to a stop, right? And so this thing here is 0. So maybe you notice that while you're reading the question, you put down as v2 equals 0. If not, if you're ever missing a variable, listing all 5 and just it'll direct your attention towards the one that you have, the 2 that are left that you have to try and glean out of the situation and realize you know them, all right? So all those things just listed as usual. What do they have here? This analysis here of the initial velocity being in the positive direction and our accelerations in the negative direction. That means you're slowing down, right? That's from grade 11. So we're going to pick an equation. And so to start out with, it's just velocity and acceleration in time. It's really just the uniform acceleration equation, right? So if you were to do the UASM trick here, you'd be circling the I don't really want to do here because I'm not going to leave this in front of all this stuff. But I mean, that would be this equation here, right? So I'm just going to undo all that stuff so it's not in the way going forward here. But it would definitely be the uniform acceleration equation. Press pause, put numbers in, that kind of stuff, and check and see how you're doing, right? So we've got numbers in there. We end up with, the delta t's in the bottom, so we're going to multiply, going to have to divide by delta t, right? So we're going to undo it by multiplying both sides by delta t, divide by that -4, because that's a multiplication by a -4, right? You're not adding 4 to get rid of it, you're dividing by that -4, giving you an answer of 5 seconds. So that's the answer for the first part. The second part was determine how far the boat travels while stopping. And so that's where you would go and you would look at your equation selection thing again. You'd circle, circle, circle and pick an equation. So go ahead, press pause, do that kind of thing. print out one of those things, have it available for when you're working, and hopefully pick out this equation here, right? So plug the numbers in and solve, right? So I've got rid of that thing. There we go. So square root of 20, get 400, take away 400 on both sides, multiply the 2 into the -4, divide this out by -8, you end up with a 50. Okay. Draw a VT graph of the motion, right? So we have this thing going, It's starting at 20, decreasing to 0. It's a uniform acceleration situation, so it's going to be a nice straight line. So that's all we're talking about so far, right? And as a little check, for those that are familiar with the graphing technique, area underneath the VT graph is your displacement. And so 1/2 of the base being that 5 seconds that we calculated, and times that initial height of the 20, area that triangle is 50. There's your 50 meters. Okay, this is a review of the VT graph method. Now, the reason for that VT graph, like I said, is kind of strategic here. That allows us to sort of picture what's going to happen, right? So the question is, if we didn't see the rest of that yet, if the boat continues to accelerate at a rate of -4 meters per second squared, describe the motion thoroughly, including a VT graph, particularly, as it continues, like if it were to continue, right? So if it continues doing that. So we have the first graph part, and then you just extend that line. It still has that same slope, right? Acceleration is slope. So slope, all the way along. Stays, keeps going, right? Keeps accelerating at that -4. So you can see that the velocities are going to go and start going in the negative direction. And so this is where it's, actually speeding up in reverse, right? Now we have negative velocities and we have negative acceleration, where you can analyze that and say, oh, well, that's speeding up, just backwards, right? So speeding up, that says sort of, trust me. So we've got that. And you can do questions with that, right? So it says determine when the boat is at a distance of 30 meters from its initial position. Okay. So if we were to do this, again, you grab your equation selection matrix thing and circle, and pick an equation. So by all means, press pause, do that. Could end up with this equation, just naturally. And if you did that, you plug numbers into this, and you hopefully recognize that thing is a full-on quadratic. It's got a delta t and a delta t squared, right? So you're in quadratic skills, not necessarily quadratic formula, but it's kind of obviously the quickest, easiest way to deal with it, because you want to complete the square while you're here, right? So rearrange this thing into the standard form and get your A, B, and C, plug into the quadratic formula and do some calculations, and it spits out answers of 1.84 and 8.16 seconds is 2 possible answers. Now, looking at that, we know it was starting at a velocity of 20, and we want to slow down to a velocity of 30, was it? Or distance of 30. Sorry, distance of 30. So distance of 30, what we know is that it went 50 meters slowing down. So you should be anticipating, somewhere around here, right? This is 50 meters all the way up to there. And, this is time, of course, along the scale. And it should get to the 30 before it stops, right? It's slowing and going 50 while it's going. So this answer is the one that makes the most obvious sense, right? The 1.84. We'll come back to that other one, though. You might already be thinking about, what that other one might mean. Grade 11, the parachute that you'd pull if you saw the quadratic formula. You'd say, well, let's just go get V2 first. There's a nice equation for that one. And so you could plug numbers into that and get the final velocity first, right? And so you get your final velocity, and then of course you just have velocities and acceleration. You just use your regular acceleration equation and get that same answer. Now, in this case here, let's go down here. We're getting, what's that going here? Acceleration. So this would spit out an answer of this, right? The 1.81 or 1.4 rounding errors and so on. The fact that there's actually like a like a forward velocity and a negative velocity possible might not have occurred to you. But of course, if you look at the graph, it should, I'm guessing I should say, right? So you've got this graph where you've got your forward stuff, and then we had our backward stuff. And so it should be obvious that, you're going to go slowing down, you're going to pass a 30-meter point, and then you're going to get back to that 30-meter point when you start going reverse. And the symmetry in this situation is you have the same acceleration and so on. You should be expecting that these two areas are both that 20 meters, I guess, right, to get back to depth of zero and back to the zero velocity and then back to that 30 meter spot when you're going reverse. And so the times here would also be symmetrical. And so if that's the case, then you also have the velocities would be symmetrical. So whatever the 12.6 number was, that's going to be the minus 12.6. So definitely a little trickier to kind of notice that it's a possibility when you do this method. But the quadratic formula spit out that number for a reason. You put that minus 12 in there, that other possibility that you get to the 30-meter spot while going in reverse, the minus 12.6, there's your 8.16, right? So that is, that's pretty cool. It works nice. Now, definitely harder to notice this, whereas the quadratic formula spits it out on purpose, right? So this one was while slowing down, right? So while slowing, I should just slow down right the first time. While slowing down and going forward still, right? And then this is while reversing, let's say, or whatever. Right, on the other way, on the way back. Okay. So, and that should be good. Hopefully, the other thing that I want to show for this one is sometimes you're going to have like a kind of compound questions. This one was a compound question too, really had sort of multiple parts. But this last one here that I'm going to go through, kind of like if you remember from grade 11, you might have seen a question where there was a horizontal tennis ball hit horizontally, and the question was like, how far does it clear the net by? It certainly wasn't just your standard, how long does it take to land and how far over does it land and so on. You have to really think your way through the situation. And this one's kind of like that. So, like if we go through, I have it ready to go here and we'll look at those whole numbers for the steps here. But we know some things, right? So we've got an initial velocity of 75, maybe you paused and read it, right? But we had an initial velocity of 75 kilometers per hour. Red flag there is always in meters and kilograms and seconds in science, right? So from grade 11, Google it if you want, whatever, but you divide by 3.6 and you convert to that smaller number of meters per second. I always remember that meters per second is faster than you'd think. Someone says, can you run like 10 meters per second? Yeah, it's just a 10, doesn't sound that big. Then you multiply by 3.6 and be like, ooh, it's a lot, right? So 36 kilometers an hour, I don't think I can do that. So the 48 meters ahead thing is that stop vehicle. We have an acceleration rate given. In this question, it said, acceleration is south. In other words, you're going north, acceleration is south, it's backwards, right? So it's obviously in opposite directions. You can use negatives if you wanted. And so really I could add that in here where i.e. this is negative 4.80 meters per second squared north. Right. Anyways, if you're just analyzing this, you have really some amount of constant velocity until you start. So this VT graph should make sense, right? Some amount of constant velocity until you start hitting the brakes, right? So constant velocity section, and then you start hitting the brakes. So really, you can just go ahead and calculate the stopping distance once you start hitting the brakes, at least, right? And that would just be, in this case, I have it done just by uniform or the VT graph method. But either way, fine. Or did I do that? What did I do? Yeah, so you had the 20.8. I guess it didn't. What was my order of operations here? 1, 2, 3, 4. I should just do it from scratch instead, really. But the while you're stopping, right, you've got this 28 point, your height of the triangle, and you want to know the time. And time you can figure out just with a uniform acceleration analysis. So you've got decreasing velocity to 20.8, you've got an acceleration, so you get your time. So this would have been, this part here would have been done first, and then that time to get your displacement. Of course, you could just use the bulkier equations if you wanted. But long story short here, it goes 45 meters while slowing down. So then you're looking at it and be like, well, 48 total to get there. In the question, it says, you came to a stop just in time. Like your bumper nudged up against the bumper, the car was stopped ahead. And so basically you're saying, okay, well, then that extra 3 meters, it must have been something you traveled while reacting. So now you have a simple uniform velocity question where you have your velocity of 20.8 and you've got the displacement of 3 that you must have traveled and you solve for time. And so that gives you a 0.144 second reaction time. So sorry to read through the question a little more at the beginning. It's already familiar to me, but I'm hopefully pressed pause and read it and so on. All right. So that is it. There you go. I was going to talk a little bit about like some of the other things like I have in here, there's, if you need some review of one-dimensional vector stuff and so on, look through that. And notice on the page here, it says, if you want more regular uniform acceleration questions, practice in the textbook that's posted on the D2L site, the e-learning site. You can do those as well. There's a lot of other stuff in sections 1.2 and 1.1 and 1.2, I think it is. But we'll start to tackle some of those as we go. But it wouldn't be a bad idea to look through that section 1.1 and 1.2 and just familiarize yourself with it as much as you can, so that when we get to it or either need it or review it, you'll be in good shape. All right, so that's it for now. Talk to you later. Let me know if you need any help as per the orientation video that's will be posted and so on. Okay. All right. See you later.